Hey class, what's happening? All right, so let's give it a shot here. I'm trying my first, little video thing. Let's see if it works. You got to bear with me. It's my first time, so it's probably not going to be perfect. This is really just for me, but if it helps you in the meantime, all right, cool. All right, so let's give it a start. I want to go over problem 16 from the homework, the related rate problem. All right, so here we have a growing sand pile. Sand falls from a conveyor belt at the rate of 10 meters cubed per minute onto the top of a conical pile. The height of the pile is always 3/8 of the base diameter, magically. How fast are the A, height, and B, radius changing when the pile is 4 meters high? Give your answer in centimeters per minute. All right, so for this problem, what we want to do is we always want to start these with an equation we always know true. All right, so here we are talking about volume. This meters cubed is going to be our giveaway that we're talking about volume, and we're talking about a cone. Okay, so you may remember back to your geometry days, but you probably don't, so let me remind you. I wrote this on the board in class. The volume of a cone is 1/3 pi r squared times height. So I always remember cones and pyramids are 1/3 the volume of their respective prisms. Okay, so that's the equation that's always going to be true. All right, now let's figure out what else is given to us. All right, the height of the pile is always 3/8 of the base diameter. All right, so the height is 3/8 of the base diameter. All right, or later on they're going to be talking about radius. So knowing that diameter equals 2 times the radius, the height is going to be 3/4 the radius. Okay, so that's a little bit of magic thing that we throw in here. That doesn't happen in real life, but we're asking that to happen so we can do the calculus. Okay, so instead of having two variables here, having an r and an h on the right side of the equation, we're going to do a little substitution so that we only have one variable. Otherwise, we have to do the product here, which we could do, but let's make it a little bit easier on ourselves. So let's say volume equals 1/3 pi r squared, and we'll substitute in for h as 3/4 r. Okay, let's do a little simplifying, make our life easier. That 3 and that 3 will cancel, and we will be left with 1/4 pi r cubed. All right, so here's an equation that's always true. Remember, we don't want to substitute anything in until we have taken the derivative. All right, so now let's take a derivative on both sides with respect to time so we can figure out how the volume is changing with respect to time. And then if we take the derivative over here, we will get 3/4 pi r squared times dr dt. Don't forget the chain rule. And we can figure out how the radius is changing due to time. Okay, so here is our derivative. Now we can start plugging some stuff in. All right, so they give us dv dt, right? They give us the rate at which the volume is changing. So dv dt is 10. 3/4 doesn't change. Pi doesn't change. Radius. They give us that the height is 4 meters, but they don't give us the radius. But no problem. We can figure that out right here. Okay, so the height is 4. So we can solve for the radius. The radius is 16/3. All right, so 16/3 squared. And dr dt, we don't know, but that's what we want to solve for. Okay, or at least for part B, that's what we want to solve for. All right, so let's give this a go. Silly me, I did not bring a calculator. So I am very convinced that you guys will be able to figure this out on your own. You'll be able to get dr dt. Sorry about that, guys. But you can do that on your own. Part A, though, they ask for how the height is changing. We figured out how the radius is changing. What we could do is go back here, where we plugged in for h, and instead of plugging in for h, we could plug in for r, and we'll have an equation with just h's. Better yet, we have this easier equation to take the derivative of. So we can do this. Derivative of h with respect to time equals 3/4 of the derivative of r with respect to time. That's much easier, right? So we can take whatever we got here, when we solved for the rate of change for the radius, and plug that in right here, and we can get the rate of change for the height. And that kind of makes sense, right? If we know the height is always 3/4 of the radius, then that means that the height will grow 3/4 as fast as the radius. So the rate of change will be the same. Okay, so that should give us our answer. The one thing we need to be careful of is this 10 was given in meters cubed. And so when you solve for this dr dt, that is going to be in meters per minute. But they ask us to convert centimeters per minute. But we're very smart. We remember that there are 100 centimeters in 1 meter. So you can do that conversions. All right, guys, let me know how this worked out. If it works out, I'm putting Miss Roshan out of business. See ya.